So, welcome back to our video lectures on projective geometry. Last time I introduced the general framework for Cayley Klein geometries, and this time we will in detail look at the measurements that you get from Cayley Klein geometries on a line if you consider distance measurements. So let me just recap what we did last time. Last time I showed you how to define the measurement between 2 points in a Cayley Klein geometry. You need a conic as a fundamental object, and you get the distance from P to a point Q by calculating the cross ratio of P and Q with respect to X and Y, where X and Y are the intersections of the join of P and Q with your fundamental conic, and you have to take the logarithm of that to turn it into some additive measurement. And I showed you some fundamental facts that essentially tell you that distances behave in a reasonable way. I also told you that if you are on a line, you have to consider your distances as a kind of oriented magnitude, and that depending on where this intersection line is, you have to consider 3 different cases. Either both intersections X and Y are real points, or they coincide, or they are complex conjugates. And I also told you, be careful, everything is only defined up to c distance times 2i pi, which comes from the multivaluedness of the logarithm. So, I have to warn you in advance, this lecture will be somewhat technical because we want to work on the quantitative behavior of this kind of measurements for really concrete situations. So I really want to focus on what happens along a line, and I want to analyze the 3 different cases of X and Y, both distinct and real, X and Y complex conjugates, or X and Y coinciding and real. For this, we consider everything happening on a line, so we can think of that line as an RP1 and calculate with homogeneous coordinates of given by vectors of a size of 2. And so the first thing I want to consider is I want to consider the situation that X and Y are distinct and real, and up to projective transformation I may assume that they are located, if this here is the real axis, at points -1 and 1, and here you see my coordinates in the standard embedding. And you know you can fix 3 points in projective geometry, so up to a projective transformation you may even consider this point P as being moved to a special coordinate 0 here. So essentially the only coordinate we have to care about is the one of our second point. Little disclaimer, the image that you see here is kind of symbolic, so it doesn't represent the real position of those points. Now what we want to do is we want to consider a situation where we walk in unit steps. So I told you, you get the distance between 2 points by taking the logarithm of the cross ratio, and now we say, well, this magnitude should be identical along a whole sequence of points, which is the same as saying that the cross ratio itself is constant. So we want to consider a sequence of points P0, P1, P2, P3, and so on, with the property such that from one point to the next one we have the same cross ratio. And without loss of generality, we may assume special coordinates for X, for Y, and for our point P0. So let's see what we get. Let's first calculate the cross ratio that defines the step from P0 to P1. So you see you have a 0 here, and as a matter of fact, the cross ratio with the 0 here turns out to be just a fraction of that type. So our unit step that we make here corresponds to this value that I calculated here. If you don't believe it, please press the stop button and check the formula. I must say it took me about a day to get the signs right in that lecture, and I'm quite convinced that the signs and the way how denominator and numerator are distributed are now very correct, but I didn't want to bother you with all the technical details here. I really wrote down sometimes just the final results. So if you calculate this cross ratio, you get this number. And let's call this number alpha and compare it to the cross ratio that you get from P0 to a point pk here. And if you do that, you see, well, you get essentially the same thing, but the coordinate here should be pk. But then I told you, you walk in unit steps along that sequence of points. So the distances add. So you get 1 times the distance, twice the distance, 3 times the distance, and so on. And for the cross ratio, this means that the cross ratio are raised to the case power. So you get this nice relation between the position of the point pk and the case power of our magnitude alpha. Now you can simply take this equation that we have here and reformulate it and see how pk depends on alpha, and you get this formula which gives you a quantitative description of where your points are really located. So if you have fixed x, y, p0 at some position, and if you have your point p1 located at some point, then this sequence here gives you the sequences of the pk. And now let's read for a second in that formula. So if you look at it, it's a quotient, and in that quotient you subtract something in the numerator and you add something in the denominator. And this alpha here, if your point p here is between -1 and 1, will be a number that is smaller in absolute value than 1. And so if you take the case power here, this will get smaller and smaller and smaller and smaller, this alpha to the k, which means that this fraction here more and more approaches the limit case 1, but it will never surpass this limit case. And I've written a little animation here. Here you see really what really happens if you calculate this sequence of points. You see how your points get closer and closer and closer to this limit situation. If you go to the other side, they get closer and closer to the other limit situation, but they will never surpass it. So this kind of measurement is called a hyperbolic measurement, and we will later on see that this is the distance measurement that we get in a so-called hyperbolic geometry. So let us come to the next situation, and this now will become a little bit tricky. So this time we consider the case that x and y are complex numbers and distinct, and by that they have to be complex conjugates because they come from real equations. Again, without loss of generality, I can put them to special coordinates, and the special coordinates I choose is this coordinate for x and this coordinate for y, where I introduced a -I and an I here, which is the imaginary unit. you may recognize that the way I did that here, the points I and j pop up that we had in our slot about Euclidean geometry. Before we go to the walking in unit steps thing, let us first have a look at the cross ratio for arbitrary points P and Q. If I calculate this cross ratio here with x and z, what I get is this expression, and if you look at it, you see that in the numerator and in the denominator you get two numbers which are complex conjugates of each other. Here you add I first and subtract I second, and here you subtract I first and add I second. So these two numbers are complex conjugates. If you divide a number by its complex conjugate, what you get is a number of absolute value 1. So you get a number on the unit circle, so you can consider this to be a number on the unit circle specified by a certain angle, and I intentionally put a factor 2 in here. You will see in a minute why. And I want to prove that this angle that you get here is really something that you can interpret geometrically. And what you get is actually the following thing. Just consider this here as, well, the standard embedding in the two-dimensional plane. So essentially this line here is located at some y equals 1 altitude, and now consider the unit circle in the two-dimensional plane. So I'm mixing at the moment complex coordinates and real things. Don't be confused about that. Just think the unit circle and think of those coordinates you have up there. Then what happens is that if you take the center of the circle and draw a ray to P and draw a ray to Q, then the phi that you get in this expression exactly corresponds to the angle between those two lines. Now I want to show you that this is really the case, and to see that, let us consider this small yellow point I've drawn here. So we are in projective geometry, so we can scale down our points in homogeneous coordinates by an arbitrary factor. And what I claim is that if you have this cross ratio here, then you get your point Q1 by simply scaling up this point here. And now again I make some without loss of generality assumptions to make my calculations a little easier. I assume that P is located at the 0 position, and I can do that by projective transformation. And now I have my point Q still sitting here, and I want to get this angle thing. You may for a moment think about, is it really okay to have everything here without loss of generality? Actually, if you don't like the without loss of generality argument, you can assume P was at some other place and you dissect it in two pieces using additivity, which leads to the same argument. So now we want to see that for that situation, the cross ratio really corresponds to that angle. So P has these coordinates, and up to scaling common scalar factor, what I've drawn here, if everything is correct what I say, has coordinates sine phi cosine phi, which is this point, and scaled up by a sum factor which doesn't influence our cross ratio here. So we have to check that if we calculate the cross ratio of those points here, you indeed get this angle here. And just one little remark here, you may again be a little confused that the sine is on the top and the cos is on the bottom of that. This comes from our uncommon choice of the coordinate system, that I want to have a 0 angle at the vertical point of the circle. So if you increase the angle, you walk in that direction. And I mentioned that it took me quite a while to get the signs right in that lecture. This was one of the reasons for that. Okay, let's calculate the cross ratio. I've written down the determinants, and you can check that if you calculate that, you end up with this expression here. Again, if you don't believe it, press the stop button, check the equations. If you look at this expression, you see that, well, I have a minus sign here, I have this angle here, and everything here looks like a number on the unit circle up to a certain factor. And well, by multiplying this equation with I and shuffling the signs in the right way, you really can see that this fraction here is the same as this fraction, where I've written a complex number on the unit circle in the numerator and in the denominator. And so after all, you can write this really as e to the I phi divided by e to the minus I phi by its conjugate. So you divide a number by its complex conjugate, and what you get is a number on the unit circle which has twice the angle, and this is the reason why I introduced this number 2 here. So what did we prove? We proved that if you calculate the cross ratio here, you get this number which really encodes this angle here. So it's exactly what I've claimed. So now let's start the walking in unit steps procedure. What does walking in unit steps here mean? Again, well, always having the same cross ratio from one situation to the next. So I want to calculate a next point here that has exactly the same cross ratio between these 2 points as the cross ratio between these 2 points. But the cross ratio we just showed is this number on the unit circle, and adding lengths corresponds to multiplying cross ratios, which means we just add the angle here once more, and with the next unit step we go even further. So I've chosen a 30-degree angle here, so in the next step we will have a point which is far out in this direction here, and then we will come back from the other point and get this point. And well, as I said, I chose 30 degrees. After 6 steps we are back where we started. So you see, distances in this kind of measurement is like walking on a big circle. And let me just write down the formulas. Again, consider this time we have a sequence starting with a point P, which is our P0, then a point P1, then a point P2, then a point P3, far out in that direction, then a point P4 and a point P5. And the sequence of points that we get here is simply one that we get from the cross ratios, where the cross ratio is the multiple, the case multiple of the angle. You can also calculate the corresponding positions of the points P1, P2 and so on, but it's easier to think of them as positions here on the unit circle. So again, I've written a little animation that shows how the real quantitative measurements really happen. So here you start with a 0, this is 1 unit step, and you go 1 step, 2nd step, 3rd step, and so on. You go out to infinity, come back from the other side and start to circle again. This measurement is called elliptic measurement, and it will, as you may guess, occur in so-called elliptic geometry. So let me now start to move these points. So let's move that point a little closer, you see the steps still get faster and faster. If I make it big, you see it wraps around several times. Well, that happens if you walk in big steps along a large circle. And here I stopped at some situation which looks more or less somehow equally distributed. So now we understand the first case, and we understand the case where both of them are complex numbers. What's left is a situation when these 2 points are identical. So we are in the situation that the line on which we measure is in a situation that it only has one double intersection with the fundamental object. So what happens here is somehow a little bit weird. So what we get if you have the situation that x equals y, the cross ratio will always be 1. And the logarithm of 1 is always 0. So the distance between these 2 points will always be 0. So no matter which 2 points you take, if you make the Cayley Klein measurement, the distance at the end will just be 0. The reason for that comes from a fact that may have puzzled you even a little bit earlier. So you measure the length, and independent of comparison to some kind of scale, you got a fixed value. And we know from our world that usually if you measure the distance between 2 points, you really have to use a scale for comparison. And actually this is what happens in this case. So let me do a little metaphor here. And this is a picture taken from the Perspectives of Projective Geometry book. Consider this little person here. And well, assume he lives on a really big planet, and at some point he starts to walk in one direction in unit steps. And perhaps the planet is so big that this person assumes that it just goes infinite in one direction. I call that person Columbus 1D. Well, Columbus 1D is convinced that it doesn't go to the infinite in one direction, and so he starts walking and walking and walking, and you've seen I've drawn a slightly curved planet, indicating that after a really huge number of steps he will actually come back. So, but now this situation corresponds to the case where we don't have a kind of absolute length measurement with respect to the size of our planet, where the planet itself is infinite, and then he really won't come back. He will walk in one direction and never come back. And this is actually the situation that we get here, and we could ask, what should we do? And what we should do, we should compare distances to each other. So assume we have our distance we want to measure. It turns out to be 0, but we can compare it to another 0 measure between a point and a kind of unit distance to A. So consider this here to be kind of unit distance between these 2 points. And well, we would divide 0 by 0, and this wouldn't make sense. But what we can do, we can consider the limit situation where x and y is not the same, and where we go to the limit situation that they actually are identical. And it turns out that the quotient of the distances is still a nicely defined magnitude, and this is what we will do next. So how do we do this change of x and y that we pass through the limit situation? Well, consider this choice of x and y, and consider alpha running between 1 and -1. If you do that for 1, you get exactly the hyperbolic case, and if you do it for -1, you get the elliptic case. And in the limit case, when alpha passes through 0, we get the case where those 2 points agree. It's like taking our calculation line and our conic and moving the conic up in a situation that you will pass through the tangency. So let me do the calculation, and now I really need the logarithms here. I want to calculate the cross ratios for my x alpha and y alpha, and what I get is this situation, and on both sides I take the logarithm. And now I want to compare lengths, and first I bring this here in an additive form, so you divide here, which turns to a subtraction of the logarithms. And if you compare lengths, you want to take this expression and divide it by what we had as a unit length here, and you want to see what happens for alpha goes to 0 in the limit case. And I don't want to bore you with calculations that you get here. You can read them up in the perspectives book, but if you apply the rule of L'Hopital, you will find out that after quite a lengthy calculation, you just end up with an expression q divided by a. Now let's interpret this expression that we get here. Well, if you have a point q, the distance here is just the quotient of those distances here, which simply means that you have our usual Euclidean measurement of distances as we always have on the real axis. So this limit case, which is at the first kind a weird special case of Cayley Klein geometry, turns out to be in the limit case to be what we always did, our usual Euclidean measurement. And so if you make these chain of points, then you really get points that are equally distant. And again, you have written a simulation here. So here is what happens. You simply have your point and go in unit steps in one direction, and you go to infinity and you will never pass through infinity, and the same may happen in the other direction. And this looks very, very close to elliptic measurement. The only difference is that in both directions our limit point, the point at infinity, is just the same point. In hyperbolic measurements these were two distinct points. So this measurement is called parabolic measurement, which means it's somehow between hyperbolic and elliptic, and sometimes, for natural reasons, it's also called Euclidean measurement. So let me wrap up at that point. So we learned that there are three different cases. They correspond to the situation where the fundamental object intersects our line, bypasses the line, or just hits the line. And in this case here we get the situation that if we walk in unit steps, we won't go beyond a certain boundary. Here we will go through infinity and come back from the other side, and here we will go in unit steps and just get stuck at infinity. And these three types of measurements are the ingredients from which general Cayley Klein geometries are built up. So you may in a specific Cayley Klein geometry be in one of those cases here, and similarly for the angles. So all in all you get kind of 9 different kinds of combinations, and in our next lecture we will explore these 9 different kinds of Cayley Klein geometries and see what's so special about each single of them. See you there!